So this is part 2 of chapter 10. We left off on this slide. We'll move forward. Synthesis of secondary alcohols. Again, we're going to use a Grignard reagent. In the presence of aldehyde, if we look at this, this would be R minus MgX plus. Your electrons from here attack the carbonyl carbon. Electrons go to the oxygen, making the alkoxide, and then in the presence of H3O plus, it's shown here, it'll form the alcohol. So here's the H3O plus. Sorry. Here, electrons from your oxygen, from the alkoxide, will pluck off hydrogen, quenching the positive charge, generating your secondary alcohol. Synthesis of tertiary alcohols. Again, I'm not going to draw everything out here since I drew it just previously. So we'll attack. Electrons go to the oxygen, generating the alkoxide. This will then pluck off a proton, generating the tertiary alcohol. So for problem 2, show how you would synthesize the following alcohol from the compounds containing no more than 5 carbon atoms. So how do we generate this? Well, one way is to take a ketone in which you have either the methyl group and the cyclopentane group, and then react it with ethyl magnesium bromide in ether step 1 to protonated water, or you can generate that same product by taking cyclopentane ketone with the ether and then add methyl magnesium bromide in ether and solvent to get the product. So in the previous 2 examples, you had more than 5 carbon compounds, so there is a third option. The third option would be to have the methyl and ethyl on the ketone, and then having the cyclopentane magnesium bromide. In this case, they don't exceed the 5 carbon rule from the original question, and so in the presence of ether and protonated water, you generate a product. So this would be preferred. So, important thing to note is that you can use step 1 and step 2 above and below the arrows in a single arrow to show that there's 2 separate steps. Grignard reactions with acid, chlorides, and esters. You can use 2 moles of Grignard reagent. The product is a tertiary alcohol with 2 identical alkyl groups. Reaction with 1 mole of Grignard reagent produces a ketone intermediate, which reacts with the 2nd mole of Grignard reagent. So to kind of show it in actual reactions, 2 equivalents of Grignard reagent shown here in the presence of acid chloride and ether and protonated water. You'll have addition twice occurring, as a result forming a tertiary alcohol. You can also do the same in the presence of an ester. In the presence of an ester, again, it'll attack, this will kick off, and you'll generate the tertiary alcohol. In terms of mechanism with acid chlorides, so again, the Grignard reagent separated as R minus MgX plus. Electrons from that will attack the carbon, kick off electrons to the oxygen, and then this intermediate is formed. However, since chlorine is a really good leaving group, electrons from the oxygen will come down, kicking it off, generating the ketone and the chloride. The ketone then reacts with the 2nd equivalent of the organic metallic, in this case the Grignard reagent again. Electrons go to the electrophilic carbon, kick electrons from that double bond go to the oxygen, forming the alkoxide. And then in the presence of protonated water, again, you're going to pick off that proton, generating your tertiary alcohol. In terms of mechanism with esters, again, nucleophilic attack, electrons kick off to the oxygen, then this is the intermediate, this is a good leaving group, electrons from the oxygen come back down, form the double bond, kicking off the alkoxide, generating the ketone. Ketone, so in this case, chloride is not being expelled, rather OR minus is being expelled. Now, the ketone will then react with a second equivalent. Again, electrophilic carbon, electrons from the double bond goes to the oxygen, forming the alkoxide. And then this will protonate from H3O plus, forming the tertiary alcohol. Grignard reagents can also add to epoxides, or ethylene oxides. So here it will attack, kick off the oxygen, forming the alkoxide in the presence of protonated water. This will pluck off a proton, forming the primary alcohol. Butyl magnesium bromide, again, attack the epoxide, kicking off the electrons to the oxygen, forming the alkoxide in the presence of protonated water. It'll pluck off proton, forming here your alcohol. So Grignard and lithium reagents will attack epoxide. These are also called, in addition to ethylene oxide, they're called oxiranes. They open to form alcohols. This reaction is favored because ring strain present in the epoxide is relieved in the opening. The reaction is commonly used to extend the length of carbon by 2 carbons, right? So you're adding 2 carbons to the product. Yes, an important thing to note is that the reaction of the Grignard reagent with an epoxide is the only Grignard reaction we've seen where the new OH group is not on the same carbon atom where the Grignard is formed. In this case, the new OH group appears on the second carbon from the new bond. There are limitations of using organometallics. Grignards and organolithiums are good nucleophiles, but in the presence of acidic protons, this is important, they will act as strong bases. So shown here, any acidic proton that you see, instead of adding as a nucleophile, they're going to serve as a base and deprotonate. In the presence of multiple bonds with strong electronegative element, the organometallics will act as a nucleophile. So things with carbonyl, cyanose, this is triple bond, S double bond O, N double bond O are examples. Reduction of carbonyl. So the hydride reagents that I add H- hydrides reduce carbonyl groups to form an alkoxide ion with no additional carbon atoms. Protonation then gives the alcohol, so reduction of aldehydes usually gives primary alcohols, reduction of ketones, secondary. So hydride reagents, you've seen these before, at least you've seen sodium borohydride before. Another reagent that's like sodium borohydride is a lithium aluminum hydride shown here. These are called complex hydrides because they don't have a simple hydride structure, such as 1 sodium and 1 hydride or 1 lithium and 1 hydride. The bonding to metal makes the hydrides more nucleophilic and less basic. So, sodium borohydride, which you've seen before, is a source of hydrides. It attacks carbonyl carbon, forming an alkoxide ion. Then the alkoxide ion is protonated by dilute acid, only reacts with aldehydes or ketones, not important with esters or carboxylic acids. Can reduce a ketone or aldehyde in the presence of an acid or an ester. So let's look at a hydride reduction. So you're going to, with sodium borohydride and with lithium aluminum hydride, they're essentially a source of H-. What happens is it attacks the carbonyl electrophilic carbon. Electrons go to the oxygen in the presence of ether, forming the alkoxide ion. Then in the calcide ion and just in water, it'll pluck off that proton from water. Electrons go to the oxygen, forming the alcohol. So it's a two-step reaction. You have an ether. In the presence of ether and just the hydride, you form the alkoxide and then you protonate to form the alcohol. Examples of sodium borohydride reduction. Here's sodium borohydride in ethanol. So here's the aldehyde in the presence of the sodium borohydride, just forms the alcohol, right? Here's butane 2-one in the presence of sodium borohydride and methanol, forms butanol. Lithium aluminum hydride, these are much stronger reducing agents than the previous case, sodium borohydrides. They're extremely dangerous to work with, reduces ketones, aldehydes into the corresponding alcohol, converts esters and carboxylic acids into the primary alcohol. So this is the key difference. So in the previous case, sodium borohydride wasn't able to reduce esters or carboxylic acids. However, in the case, because lithium aluminum hydride is a stronger reducing agent, you can take esters and carboxylic acids to the primary alcohol. So reduction with lithium aluminum hydride, it's two steps. One is lithium aluminum hydride in the presence of protonated water. So we'll take this ester all the way down to the primary alcohol. And the mechanism is similar to the attack on Grignard esters, in which you have the hydride come in, kick off, take it off, and then again come in once you have the ketone, and then form the protonation. Important thing to note is that lithium aluminum hydride and water are incompatible. That's why water is added as a separate hydrolysis step. It's really key. An explosion or fire would result from the process if you just did not add number 1 and number 2. So you must add those two numbers in order for this to work. In terms of reducing agents, sodium borohydride can reduce aldehydes and ketones, but not esters or carboxylic acids. Lithium aluminum hydride is a stronger reducing agent and it will reduce all the carbonyls. So here's a nice picture. Here's a comparison. Here's an ester in the presence of sodium borohydride. Only the ester portion doesn't get reduced, only the ketone part does. So you generate this product in the presence of lithium aluminum hydride. Both this and both this gets reduced all the way down to the alcohol. Catalytic hydrogenation. Hydrogen in the presence of Raney nickel. Raney nickel is a hydrogen-rich nickel product that is more reactive than palladium or platinum catalysts. This reaction is not commonly used because it will also reduce double bonds, right? So Raney nickel will reduce double bonds and triple bonds in the molecule, so you want to be careful about that. But if you want to reduce those as well as the ketone or aldehyde that are in, you can use Raney nickel. Selective reductions. So if we added hydrogen in the presence of Raney nickel, we would reduce both this double bond as well as this aldehyde, right? But if you want to do selective reduction and just leave this intact, right? Leave this reduced, then you would use sodium borohydride, which would only reduce then this portion. Thiols or mercaptans. Sulfur analogs of alcohols are called thiols. SH group is called also mercapto group. And in terms of name, your name by adding the suffix thiol to the alkane name. Nomenclature, so this would be methane thiol or methyl mercaptan. This will be butane 1-thiol, right, because it's 4, or N-butyl mercaptan, and this is mercapto ethanol, so write ethanol and then 2-mercapto ethanol. So common names are formed like those of alcohols using the name of the alkyl group with the word mercaptan. Acidity of thiols. So here's ethane thiol. It has a pKa of 10.5, and so it's pretty acidic. Then when you get to benzene thiol, its pKa drops, right, sufficiently because of resonance stabilization, right? So again, you'll have reactions with hydroxide so that you favor the production of the ethane thiolate and formation of water, or benzene thiolate and formation of water. If you compare that to just ethanol, ethane thiol to ethanol in the presence of hydroxide, you form the ethyl oxide, but the reaction is now not favored going to the right, but rather favored going to the left because the pKa is lower for water. So thiols are in general are more acidic than alcohol. In order to synthesize thiols, what you can do is use sodium hydrosulfide. This is an SN2 reaction in which it'll attack the carbon center, kick off the alkyl halide, or the halide part, which is a good leaving group, forming the thiol and the salt. So yeah, thiols are commonly made by SN2, so primary alkyl halides work real well. To prevent diallylation, you want to use a large excess of sodium hydrosulfide with the alkyl halide. So thiols can undergo oxidation. Here's an example of 2-cysteine residues. In the presence of oxygen, actually from air, you can have formation of a disulfide bond, shown here, and water. Elimination is the byproduct. Now, if you can actually go in the opposite direction by adding a reducing agent, which will then cleave that the disulfide bond to generate the thiols. So this ends chapter 10.